Hello, welcome to part 2 of my ME532 final project video. This is the part where we discuss all of the different functions that allowed me to execute the pick and place maneuver of the series of boxes that I illustrated in the demo in the first video. I'm Alex Liskey, and we'll get into it. We'll start by highlighting the user input section. Here we have box positions and drop positions, two variables that are essential. For every XYZ coordinate in box positions, we'll later initialize a box to be placed. And similarly, in drop positions, we'll decide where the robot is going to drop the box that was initialized in the same element from above. So for example, this box is going to be placed in this position, this one in this position, and down as many as you'd like. I'm initializing these boxes and these positions with loops so that this variable is infinitely expandable theoretically. And that way the user can include as many boxes as they would like. Next, we will initialize the scenario objects, which is just MATLAB's way of describing the world and describing collisions and sort of automating lots of the collision checks that can be done in the various scripts. You can see that I add a bunch of the obstacles here. We've got the 3 cylinders from the video and the boxes that serve as the platforms and the wall. Here's where I import the robot. This is code that I took from the MATLAB tutorial illustrating how to use scenarios that I've linked as a reference in my report. But this is our first helper script that we'll talk about later that just, initializes some of the robot objects that's later used. Next, we're going to initialize the boxes with the for loop that I mentioned. We're going to initialize 1 for every element in box positions, and we're also going to update some variables that keep track of how many boxes need to be moved and where they're located, etc., etc. We do some more cleanup with setting up the scenario, doing a first initialization, and moving the robot to its, what I'm going to call its initial configuration, or colloquially home position. Now, this large code block is the main for loop where all of the boxes are going to be picked up and placed one by one. So we start out by keeping track of the current configuration, and that allows us to really easily streamline the movement scripts that I use later. So starting from the top, I pick up each box, and this is the coordinate of where the end effector is going to be, and this is the orientation of the end effector. And I run my second helper script right here to figure out what that configuration is going to be. And next, like I discussed in the video, I have a check to help prevent collision that just edits that basically adds a waypoint, an offset of pi/8 above where the final hand is, or the final end effector position, so that it can cleanly pick up the box. And based on how the solver decides to approach, you either want an offset of plus or minus pi/8. The pi/8 is kind of arbitrary, but I just found that it was a nice balance between giving yourself sufficient room to pick up the box, but also not so large that it could cause world collisions by taking up too much space. I also have a helper script to operate the movement. This is the script that basically updates the plot that you saw and changes the robot's position to make it look like a video stream, but in reality I am simply updating the plot with all of the different robot poses as they come up. And I call this script basically anytime I need to move. But first I have figuring out where the box is going to be, moving to that first waypoint above the box, picking the box up, and attaching the end effector to the box, and finally moving to the box drop location and detaching. And we keep the plot updated throughout the whole time, and this for loop runs continuously until we reach our final destination, at which point we run a movement to move from the last drop configuration back to the home position, as we saw earlier. Now to the helper scripts. We've got this function where all it does is properly load the robot, because the author of the tutorial saves us some headache with potential self collisions that the robot has in its standard import form. But the way they solve it, I actually needed to change it back. What they did was there was a constant self collision between the final link and the second to final link, so that it would always throw an error and always think that it was in self collision. So they responded by changing the geometry of the collision mesh to a rather large cylinder, an oversized cylinder. And that basically gave me unnecessary world collision errors. So what I did was I switched this collision back into a box that more represented the proper geometry. And I talk about this in the report, but it allows me to sneak in between those two cylindrical obstacles that I have on I believe the green platform, and properly pick it up. Now we have the helper script to run the inverse kinematics. So the real meat and potatoes is right here, where we run the planner and initialize the inverse kinematics object provided by MATLAB. And most of the function is to account for, to check for and adjust in the case of world collisions and self collisions. So I talk about this in the report, but I have a number of initial seed poses to start the optimization process at. And they basically correspond to when I might want an elbow up versus an elbow down solution for my robot pose when I'm picking up or putting down a box. Because what would often happen is I would go to pick up a box behind the blue wall, and the solver would be stuck at a local minimum in an elbow down solution, which obviously would cause a world collision with the wall. Maybe I can pull out this visual aid. The robot would maybe try and grab a box near this cylinder in its elbow down position, which would collide with the wall. So I've initialized a number of seeds to hopefully coax it to avoid that. And if that doesn't work, I throw an error. And the other major thing that I added to this was when we were running the boxes through the cylinders. Remember how I talked about that the end effector would rotate based upon where the box was oriented with respect to a cylinder? So it would be oriented parallel to the x-axis if a box was here to be able to pick it up. And if the box was, over on this side, if it'll let me go there. If the box was over on this side, it would orient along the y-axis to be able to pick that up without a world collision. This is where I check to see world collisions and adjust if needed. The movement script is pretty simple. It's as simple as updating the 3D plot and making sure that I can freely rotate in 3D. But once we have a valid pickup and place configuration, I just pass in the robot, the scenario, and the plot that I want to update, and it'll automatically update for each interpolation step to give a to give a visualization that is an approaching smooth motion. As you saw in the last demo, it was choppy at some points, and I would need to expand into doing velocity control and implementing consistent time simulation steps to account for that. This final helper script was just a debug tool that you might find useful. If you run into an error, it will let you visualize the robot in the case of collision. Oh, well. This shows all of the different collision geometry that the robot has. This is the problem collision box that I had to edit in the robot import script here. This used to be a large cylinder and wouldn't be able to fit through these two cylinders. So by changing it to this long skinny box that better represented its geometry, I was able to give a better look at how that would work. So anyway, that should conclude my tech tour video. Thank you very much for listening, and have a great day. Oh.